Okay, this is the second section on material balances. We're still on non-reactive systems, so we're going to basically be looking at somewhat more complicated systems that have multiple units, and we're going to learn about splitting point, purge point, and all that kind of thing. Okay. Um, so this is an example of a multi-unit process, and I just want you to follow through on the ammonia recycle. We feed in some liquid ammonia, and we uh, we store it, and we feed it into the reactor as a liquid, and it has to be, the pressure has to be raised, but uh, we can do that. And here's the reactor that requires the ammonia, and then we send it out. It has some sludge plus some remaining ammonia. If you blow it out in here, you drop the solids, and the gas um, goes up by density, and it is vented off. And then the sludge plus some liquid ammonia comes through here, and you put it through a flash drum, and we vaporize ammonia. And there's going to be some crud in it, so we're going to do a recycle here. We're going to do a recovery process. And through this method, we are able to reuse most of the ammonia. We'll compress it and feed it back in where it is mixed with the incoming liquid, and the process continues. So this is an example of a recycle process that you would be able to do the mass and ultimately energy balances at the end of this course. So I wanted to show you a relatively complicated mass balance so that you get accustomed to the idea that this is not scary. It's just you take apart the information. So you don't have to immediately understand everything the second you look at it. You have to look for the solution strategy. And the first thing we're going to do is we note that there is a basis on the chart. This one here happens to be in kilograms. So the first thing you want to do is make all the units homogeneous. So the first thing we would do is convert this stream to kilomoles. Then the second thing you want to do is count up unknowns. So let's count unknowns on this flowchart. We have 1 here with Ym1. Here it's repeated. Here's another one, 2. And these are both repeated here, so we don't have any more there. We have O2, that's 3. That's repeated there. So that's all they have here. These are all unknowns, but let's just move on. Just do the overall balance. In fact, they're the same as on the output because everything is separated into 2 perfect streams. There's no one component that goes into both those 2 streams. But anyway, so if we look at the overall balance, we have 3 so far. Then we have y of m, and we have y of n2. Okay, and that's it in terms of components, but we also have the 2 stream flows. So we have 7 unknowns. And now let's count up the species. So if we did our degree of freedom analysis, we have 7 unknowns, and you should write down what they are. And we have how many species? We have 1, 2, 3, 4, 5, 6 species. So we have minus 6 species. And we can also get one more piece of information. These mole fractions will all add up to 1. So then we have 0 degrees of freedom. So once we have that all figured out, that we can proceed with our calculation, the next thing we want to do on this is look for solvable balances. Look for solvable balances. And you might notice that we have here, we can multiply these out, first of all, and get flow rates. Okay, we're going to have 0.33 k-moles per hour of hydrogen, and we're going to have 0.119 k-moles per hour of oxygen. And we can look at our inlet streams, okay, and we see that we know what the flows are here once we calculate them, okay. This one is actually 1.232. You'd be able to calculate that just using the molecular weight. And the water here is going to be 3.5. So the only other place on the chart that we have formaldehyde is here. So we can solve for M1. Y of M1. And once we have Y of M1, then we can get the methanol because we have that mole fraction. Okay. Then we have now, if we know how much methanol there is here, the only other place it shows up on the flow chart on the overall balance is here. So we can now find out what is the total flow of, we can't directly calculate the mole fraction, but we can calculate the flow. And once we know that flow, then we can get the flow of nitrogen. And at this point, we are going to know everything on this chart on the inlet and on the outlet. And from there, you can solve for the remaining balances that you have on the inlet. Okay, if we know how much oxygen we have here on the outlet, then we can solve for here because there's no oxygen in the gas stream. We know how much water there is here, so we can do a balance on this plus this times n.2 is going to equal this. It's actually going to equal the flow rate, not the mole fraction, mass fraction rather. And as you'll see, you can continue and solve all of these balances. So just to review this, we've counted up the unknowns, and then we solved for all of the flows on the, so we could determine that we had the molar flow rates on the exit stream. And so you solve for those.